Hi, and welcome again to my Physics Online video lecture series. Today's video, I'm going to be talking about force diagrams a little bit. At this point, you should have already watched my videos on forces and Newton's laws, and so you'll recall basically Newton's three force laws and their applications. Today, the main focus is just on drawing force diagrams and what they are and why we do them. This is kind of an important point, important enough that I'll even kind of like highlight it as an important point. I have mentioned this before in other videos, but this one's an appropriate place to maybe reiterate it and emphasize this point a bit, which is that problem solving in physics often begins with drawing a diagram. So problem solving in physics, and engineering as well actually, but problem solving in physics often, and I may even say almost always, begins with drawing a diagram. Now, there are different types of diagrams that you may draw, but the focus of today's video is one of the more commonly used and really powerful diagrams in mechanics, which is the diagrams that are called force diagrams. The most common of those is the free body diagram. Are there other kinds of diagrams that we would use in physics and in affiliated engineering disciplines? Yes. The other, maybe arguably as common or more common, would be circuit diagrams. And in physics too, there's ample opportunity to draw those. We also have diagrams that maybe involve electric field lines or magnetic field lines, etc. There are ray diagrams for optic imaging would also be another very common type. And all of these have their uses. The one that I'm focusing on in this video is force diagrams. So what are force diagrams and what do they do? Force diagrams basically just are diagrams that show what forces act on an object, and as best we can tell, what direction do they act in. So a force diagram in general shows the presence and direction of forces acting on an object or on a system, but typically on an object. And what they do is they then let us set up, for example, Newton's second law. Later on we may also use them a bit in figuring out energy, work done, that kind of thing. But they are helpful for figuring out what the net force on an object is. So Newton's first law too, actually, in statics. But it's the presence and direction of forces acting on a given object or system, obviously, is also true. And there are a few different variations of force diagrams. The probably most common at this stage, like most common when you're just learning Newton's law, is the free body diagram. So this is one type of force diagram, free body diagram. There are other diagrams that you could use. For example, later in a physics course, when you're getting into stuff like extended objects and torques, it may be advantageous to draw the forces showing the location on the object that they act. So, you can do like extended object diagrams as well. These are mostly there for like if you're trying to figure out the torque, you have to define an axis of rotation, and so you need to know where each force acts on the body relative to that axis. And so this would not be a free body diagram, but it would be a force diagram. There's other diagrams that you can draw. One of the ones that I actually fairly commonly use is, I'm not really sure what the formal name of it is, but it's essentially you can draw like a stick figure of the diagram or of the object. So you could call it like a stick figure, geometric representation, something like that. And that one is essentially it's best for if you, let's say, have like a box sliding along an inclined plane, and you want to show that that there is an object and that there is an inclined plane, but you also want to then draw forces acting on the object and treat it otherwise like a free body diagram. So it's not truly a free body diagram, but it serves a similar purpose. It just kind of adds a little more context. So what is a free body diagram for starters? I'm not necessarily, by the way, going to do all of these force diagrams in this video. So what is a free body diagram? Free body diagram, basically you represent your object as a point. So your object is represented as a single point or dot. And these work very nicely for simple, like Newton's law, Newton's second law especially, Newton's first law if we're just balancing forces and not worried about torques or rotation, collisions that are basically head-on collisions or otherwise collisions in which we don't expect there to be rotations involved, just objects colliding and either sticking together or bouncing off each other, but the motion is all translational. That's what these are best for. Your object is represented as a point. You basically can draw forces acting on the point basically as arrows, and depending on how fancy you want to be and how much you know, length may represent magnitude, if that is known, of course, and direction may or should approximate the direction that the force is acting in. So arrow points in, let's say, approximate direction of force. And these are, I guess you could say, like the simplest to draw because you don't have to have any particular artistic ability. Here's a simple example. Draw free body diagram for a book on a table at rest. Okay, so basically what you would do is you'd represent your book like this. So here's my object. It's just this little dot. And I know that presumably the table is like sitting on the ground, so I have a force of gravity. So we could label this as Fg or mg or something like that. And then also there's a normal force from the table. And so the normal force, whoops, my drawing program is messing me up a little bit, but the normal force would be like this. Some people would just write like an N for normal force here. That doesn't especially matter. But this right here is a very simple free body diagram. If we're being really pedantic, if we know that the system's at rest at equilibrium, then these two arrows should actually be exactly the same length and point in exactly the same direction. But it's not strictly necessary that we show that exactly in order to use the problem. What we've done here is we've set up, here's my object, here are the forces that act in it. We can see that they're acting in opposite directions. We can see that there aren't any other forces, so therefore, if it's at equilibrium, these two must be opposite and equal, and we can set up Newton's first law. Another example would be, what if we needed to instead draw for a book sliding on a ramp with friction? So in that case, we would expect there to be basically like the object here. We would expect again to have gravity pulling downward on the object, so Fg. Maybe my ramp happens to be in this direction, so I would expect there to be like friction in the opposite direction as the object is moving, and then I expect there to be a normal force here. Maybe one more example. So what if we have an object that has multiple forces in the same direction? So example, maybe there's like a cork in water, but a hand is pressing down on the cork. Your cork would now be this right here, and there's basically like some force upward from the water, as we'll learn in a later chapter. That's called the buoyant force, so we'll call that FB. There's also downward a force from gravity, and there's also maybe downward another force from the hand. Now, free body diagram in this particular case, where there are two forces known to be in the same direction, sometimes you can also draw it by having the buoyant force essentially pointing upward like this, FB, and then having one force from the gravity here, and you can also draw the other force from the hand here. Like this also suffices. And for that matter, some people draw these free body diagrams. This is a bit of a tangent. This is getting a little bit like a variation. You can also draw these forces like tip to tail. And you could do that with a free body diagram, but people don't usually do that. So that's kind of like drawing free body diagrams. A counter example to all these would be the sort of like stick figure diagram or cartoon force diagram. And an example of that might be essentially you draw objects or stick figures of the objects. So stick figure objects. You still draw the forces as in a free body diagram. So forces as in free body diagram. But you now have some more context for it. So for example, what might the diagram look like for a box being pulled up a ramp with friction? So you might actually go ahead and draw the ramp. You might draw a stick figure of the box on the ramp, and then you might draw in the forces, which would look basically like this: friction, pull force, normal force, gravity. And then you could change this to a free body diagram. Anyway, that's all for today.